Hello everyone and welcome back. Like I promised in the last video, this video will be about proving why it is that the Carnot engine is the most efficient engine that can be designed. With that efficiency being equal to eta is equal to 1 minus T2 by T1. So the way that we are going to proceed with this is by proof of contradiction. That is, we are going to assume that there is an engine that has an efficiency higher than that of the Carnot engine, and then we're going to prove why this engine violates the laws of thermodynamics. But before we proceed with that, I thought that I would touch upon two important things, and the first of that being what a refrigerator is. The way a refrigerator works is exactly opposite to that how a heat engine works. So in the case of a heat engine, what you do is you take in some Q1 amount of heat. So I'm just going to draw this over here. Let's assume this is the engine and this is the refrigerator. Alright. So this is going to be the reservoir. Alright. This will let it be at a temperature T1. And this is going to be the sink, and let this be at a temperature T2. Okay. So it's going to take in some Q1 amount of heat. It does some work and it lets a Q2 amount of heat in. The value of that Q2 is Q1 minus W. Okay. But in the case of a refrigerator, what it does is it takes in, say, a Q3 amount of heat from the cold reservoir, from the sink, that is, and then it has a work, say let it be W2, a work done upon it in order to release, say, a Q4 amount of heat to the heat reservoir. Now, as to why it needs some amount of work done on it in order to transfer heat. Now, the reason for that is because it violates the second law of thermodynamics, and that is the second thing that I wanted to focus on. Now, the second law of thermodynamics has a lot of statements. It has a lot of different forms of statements, but the two that we're going to discuss here are delta S of the universe, that is, which includes the system and the surroundings. Delta S universe, I'm just going to write U over here, is greater than equal to 0. And secondly was what I just stated, that is, there is no process possible which results in the transfer of heat from a colder place to a hotter place. Alright. Now, delta S universe can be written as delta S system plus delta S surroundings. Alright. And this has to be greater than equal to 0 in order for the law of thermodynamics, second law of thermodynamics, to hold true. Now, the delta S of the system, that is, hold on, where's my mouse here? Yeah. So delta S of the system can actually be written, or delta S in general can be written as Q by T by T. So this actually represents the amount of heat lost and at what temperature it is lost. So suppose you lose heat at a higher temperature, the change in entropy will likely be lesser because the molecules are already at a very high temperature. So adding or like removing temperature from them, removing heat energy from them at such a high temperature won't really make that much of a difference. Whereas adding energy to a molecules that are very moving very slowly, that is that they are at a very low temperature, will likely result in a much higher change in entropy, as that is a comparative change, a relative change is what we're looking at here. So coming back to over here, that is just not really an intuitive understanding of entropy, just to a hand waving measure of a hand waving way of describing entropies. So in order to demonstrate why this violates the law of thermodynamics, we're going to assume that there is no refrigerator, alright? So this is simply a boundary that's separating the two surfaces. This is T2, this is T1, and we're going to assume that, you're going to assume that T1 is less than T2, okay? And that heat energy is transferring from T1 to T2. So to calculate the change in entropy, we're going to look at the amount of heat that is lost at this temperature for the surroundings and the amount of heat that's gained at this temperature for the system. So if we look at that, we're going to put a minus Q here for the surroundings first. I'm going to evaluate it for the surroundings first to indicate the fact that heat is being lost. And I'm going to put a plus Q here to indicate the fact that heat is being gained. So obviously T2 is greater than T1, so this value, the magnitude of this value will actually be lower than the magnitude of this value, which will result in a net decrease in entropy, which I mean, yeah, this is going to be a net decrease in entropy, which actually violates the second law of thermodynamics. So essentially this is what we're going to prove here. So this actually shows us why when heat is transferred from a colder to a hotter place, the second law of thermodynamics is violated, and thus it's not possible. So as to why I bothered to do this here, this result is something that I'll be using in the proof today. So I thought it would be useful to look at this first. So I'm going to come back with a better apparatus that helps us to actually go on with the proof. So I'll just see you in a few minutes. Okay, so I'm actually going to begin by describing what this setup over here is. So this over here is the reservoir, which has been kept at T1, and this over here is a sink, which has been kept at T2, and of course T1 is greater than T2. Alright. Now this over here is an engine that has an efficiency that is higher than the eta, that is the efficiency of the Carnot engine. So we're going to denote this efficiency with eta, and we're going to say that this is greater than eta. Okay. Alright, so this over here is a Carnot refrigerator. That is, it takes in some heat, it has some work done upon it, and releases some heat to this reservoir over here. Now, what would be helpful is we actually got a concrete value for eta dash, which we might be able to use in our working over here. So what I'm going to do is I'm going to write eta dash. Hold on, I'm going to write eta dash by eta is equal to 1 plus x. So eta dash is greater than eta by some factor 1 plus x. So what I'm going to do next is I'm going to evaluate the amount of work that will be done by this engine over here, this supposedly higher efficiency engine, when it takes in some amount of heat Q. So we know that eta dash will be equal to work dash by Q. Okay, then I'm going to write work dash is equal to eta dash into Q, right? And then what I'm going to do is I'm going to substitute eta dash in terms of eta and x. So I can write work dash is equal to eta into 1 plus x into Q. And if you'll notice closely, eta into Q is nothing but the work done by the Carnot engine. If there were a Carnot engine in this place instead of a engine of high efficiency. So work dash is equal to work done by the Carnot engine, which I'm going to denote with C over here, into 1 plus x. Alright. So we can say that it will give out some work done as work C into 1 plus x. And this work done, that is, it is a form of energy, yeah? And this work done will actually be the work done on the refrigerator. Alright, so but before that, let's just look at the amount of heat that will be released. Now from the first law of thermodynamics, we can simply write this heat released as Q minus work done into 1 plus x, and that is the heat that is released to the sink over here. Alright, so this engine over here transfers this amount of energy to the refrigerator over here, the Carnot refrigerator. Now what we're interested in is to find out the amount of energy that this refrigerator over here gives to the reservoir. And the way that we're going to do it is using our definition for efficiency. But one thing to note over here is that efficiency is always defined in terms of the component that you're interacting with. That is, it always depends on the heat that has been gained or lost in interaction with the reservoir. It doesn't actually mean the amount of heat that the component has gained. So to make it clearer, so the refrigerator will obviously take in some amount of heat and will give some amount of heat to the reservoir over here. But we won't actually take in the heat. We won't actually take into account the heat that has been taken from the sink over here. Instead, what will be taken into account for the definition for efficiency is the heat that the refrigerator gives out to the reservoir. So in order to do that, what we're going to do here is, now we're going to write eta as work dash, because that is the amount of work that is being done on the refrigerator, by the amount of heat that it is giving to the reservoir. That is what we aim to find. So I'm just going to write that as QC. Okay, we say that eta is equal to work dash by QC. That is what we aim to find. So what we can write this as is, or instead what we can write is QC is equal to work dash by eta. Okay, now if you notice here, we already have an expression for work dash by eta. So if you take this to the other side, what you'll get is QC is actually equal to Q into 1 plus X. Alright, so we know what amount of energy the refrigerator will give to the reservoir when this amount of work is done on it. So I'm just going to write this as Q into 1 plus X. Alright, and of course from the first law of thermodynamics, we can now check how much heat was taken in by the refrigerator, and this will be this subtracted by this, so that will be actually Q minus WC into 1 plus X. Now what we want to do next is look at this entire apparatus as if it's one whole process. That is, we're going to ignore the fact that the engine and the refrigerator are two components, and in fact what we're going to just look at is the net amount of heat that has been gained or lost during this process. So what we're going to do is we're going to calculate how much heat has been transferred from the reservoir to the sink, and then we're going to calculate how much heat has been transferred from the sink to the reservoir. So let's do that. So now we're going to write the net amount of heat that has been absorbed. So first let's look at how much heat the reservoir has actually absorbed. So for that I'm going to write Q into 1 plus X. There's another Q into 1 plus X, so I'm just going to write 2 over here, and this is actually negative, so I'm going to write minus into 1 plus X. Alright, and now since this heat is being lost by the reservoir, I'm actually going to write negative, so I can write this as minus 2Q plus work into 1 plus X. So this is minus 2Q plus this into 1 plus X. Okay, so as you can see, these two will cancel, and also 2Q will cancel. So the net heat absorbed by the reservoir is actually equal to 2Qx. That is, the reservoir actually absorbs heat, which makes absolutely no sense because the heat is actually being given by this sink over here. That is, heat is being transferred from a colder to a hotter body, which violates the second law of thermodynamics. So as you can see, an engine that gives an extra amount of work over here will lead to a result that violates the second law of thermodynamics, and hence such an engine cannot be designed. So that was all about how the Carnot engine is the most efficient engine that can be designed. So that's pretty much it, and thanks for watching.